This is AP Calculus AB. We are on Unit 11, Lesson 3, and we are on our final standard for all of AP Calculus AB, and that is volume. So where are we in the unit guide? We are on 11.3. We're halfway through the last unit. We're really close to just doing review for a while. And today's lesson is about volumes of square cross-sections. So let's go ahead and get started. So volumes that we know. So this guy, and I don't want to write this down, but what is the volume of this if I have, and I do want to write this down, if I have, let's say the length, I'll do cursive L, I have a width back here, and I have a height for this shape. By the way, what is this shape called? Do you know, Joy?
Which one?
This shape right here. Oh, whoops, I did not unfreeze the screen, sorry. This shape right here.
A rectangle?
Rectangular
Prism.
Prism, there it is. Yes, it is a rectangular prism, and then to get volume, you could just multiply length, width, and height. That is what we're taught in geometry, but in calculus, you need to take it a little step further. What you could really say is, instead of length times width times height, let me write that out to the side. Length times width times height. That's really saying length times width is the base area. I'm going to do capital B for base area. And I'm going to also say that right here. So if I highlighted that area. Okay, maybe this highlighter is a little bit too large. Let's make it a little bit smaller. If I highlight, that's too small. Goldilocks right there. Perfect. That area right here of this base shape, I'm going to call him B. And that B is found by taking L and W. So really, the volume is found by taking your base area and you multiply by height. And it's really saying the same thing as this, but it's in another way. You find the base area, multiply by height. The reason I want to write it like this is because it can be applied to other types of shapes. For example, do you remember the area, or it's not the area, but the volume of a cylinder, Joy?
Pi r squared times height.
It is pi r squared times height.
Or is it 2 pi r?
No, you have it pi r squared times height. So pi r squared, that thing, I'm going to call the base, because pi r squared is just the area of a circle. So, which means if I come back and use my little highlighting tool, this area right here, I can call that B. And my volume here is base times height. It's the same formula over here, which means that if I have any base of any shape, and I can find that base area, and I have a height that just goes straight up at a 90-degree angle. It's unsaid, but this is a 90-degree angle, this is a 90-degree angle, and it goes straight up, it doesn't go at a slant. Then all you have to do is multiply by h. Which is cool because we can use this idea to apply to this crazy volume that we don't know. So I just drew a random shape here, and we can't find the volume of this at first glance, but really it's just an f of x minus a g of x between a and b. You take the integral of this function, and then you'll get the area of b, so we can say that that would be our area b. And that will be the same area b in this volume that I'm trying to find. All we have to do for this volume is the same exact thing. Volume is going to be b, which we find using calculus, times height, which they should give us. So height was right there. All right, questions so far? All right, so that's the basic idea behind volume for this lesson. We find an area by subtracting, you do f of x minus g of x, find base area just like we did in the last lesson, but now we are going to somehow find a height here. And it's not going to be as simple as just multiplying by height. It is a little bit more complex than that. And let's do this. So put down your pencil. And if you're watching the video, put down your pencil as well. I want to show you what I mean by a cross-section that has a square. So let's pretend that we have some function here, and we're not going to copy any of this down. I'm going to copy down stuff in the next slide. So that's why I want our pencils to be dropped down. Say I have this area. I want to say, how can I make a square? So what's going to happen is I want to have the distance between the red function and the blue function, and then that's going to be some height. And we can say maybe that's some height x. And then to pull out a square means I'm going to pop out a square into the third dimension, and because this little shape here is just a square, this height right here that it pops out is also x. So let's see what that looks like, and it's kind of a cool demonstration. Let's hop over here. So I have this shape, and I'm going to choose the square. You can have different types of cross sections, but today we're just dealing with squares. So what happens? As I introduce squares, you can see that, okay, I'm popping out squares, and I want all the squares all the way from 0 to where it intersects here at 1. So when I do that, and I have an infinite number of squares, remember taking the integral means an infinite number of squares, this is the shape that we get. This is the three-dimensional shape that we get by taking squares and squares and squares and squares. Of course, you'll get a different type of shape if you chose to do, it'll keep rotating. If I instead choose to do equilateral triangles, that will look a little bit different. And if I choose to do semicircles, that will also look a little bit different. But for all of today, we're just doing squares. So we'll leave it on squares. Perfect. So that should be a good visual demonstration of what we're trying to do here. Now let's actually go through the math on how to solve these. So go ahead and draw this function. All right, now that we've copied this down, you might be asking, how the heck do we draw that three-dimensional shape right here? How do we draw the shape that we found right here? And there is a way to do that. Usually you just want to draw one of those squares to show what you're doing, and I'm going to do that kind of freehand, because I'm going to use technology here. What we want to do is draw a line straight down from our blue function to our red function. And as Joy pointed out, we should be labeling these. I'll call this f of x for the blue function, and we'll say that the red function is g of x. All right, so I need to somehow make a square pop out from here. So what I'm going to do now is I'm going to make a line come out here and make it what seems to be the same length coming out, and then you can connect those to make a square. And I can fix this a little bit. This line was a little bit too long. Now it needs to go up a little bit like that. Perfect. So we have a square. But here's the kicker. What we're doing is we're not really finding area here. What we're really doing is finding volume of this tiny little region. This region really looks like this. So it's going to be a little bit extra. Let's give it some width. And this width is going to pop out as well. And it's a little bit off, but I think that we can deal with that. What we're really doing here is we're finding this little square that has volume. So it's really a rectangular prism that we're finding. While the cross section is still going to be a square, just like we said right here, volume of square cross section, that square has volume. I want to pull this shape out to the side here. So let's go ahead and redraw that shape. Actually, since we're going to do a cross section right here, let's just do that shape right here. I want to make this line a little bit thicker. That looks good. All right, so let's say we have that square. Okay, it's not really looking like a square. Maybe it should end right there. That looks better. So we have a square. And that square is also going to have volume. So we're going to make it pop out a little bit. Like in that dimension. Looks good in that dimension. Freehand with a straight edge. So
This is the last slide.
this is the last slide, yes. So what does this shape look like? So let's go ahead and label the dimensions of the shape. So let's say that this was the base that I'm talking about right here. This base right here. That means that this base is what? In terms of our x's and stuff, all of our equations, what is this thing if it matches up with this thing, Joy?
The height.
It is the height, and how do I find the height? Something minus something.
F of x is f of t.
Close. I think it's f of x minus g of x. And there's my minus sign with a different color. Yeah, I think so too. So that is f of x minus g of x, which means that this height over here on the left-hand side also must be the same thing, because this is a square. So I'm going to copy this and paste this. It must be the same right there, because it's a square. So we know that the area here is f of x minus g of x squared. So if I can put that here again, this area in here, if I put parentheses around it, the area is f of x minus g of x squared. Okay, that, remember, is our b. if you refer all the way back to our slide back here, we just found our b. We haven't found the height yet. The height here of this square, the width really of this square, is going to be the change in x. So we call this thing dx. dx. The old notation back yonder used to be delta x, the change in x, but we call it dx now. Some people still do delta x maybe. But that width of this rectangular prism is dx, to give it a volume. Which means, in order to find the volume of this region and then count up all of those regions infinitely in between a and b, we need to do the integral. Because the integral literally means add up everything between a and b. Add up all of these shapes between a and b. We're allowed to control how big d of x is, and when we take the integral, that d of x turns into basically 0. It approaches 0. It's infinitely small until it basically turns into the shape that we saw back here, where it's almost just a square, not even a rectangular prism. So how do we say that? Well, we need to do b times height, base times height. So our b here is going to be f of x minus g of x, and I'm going to do square brackets. That thing is going to be squared. That was our b, our base. And I'm going to even say that down here. Okay. Yeah, I'm going to get to that in a sec. I have to multiply it by dx after I label it. So this is the base area. And that was just one slice that we looked at. So base area of only one slice. One slice. And then in order to get b times a, or b times h, the h here is going to be dx. So this is going to be times dx. And what is dx? We'll label that as well. dx is going to be the thickness of that slice. If you would like to say width, you can. Thickness of slice. You should say width of the slice. So now by taking the integral, we have an infinite number of these slices with an infinitely small width, which means it perfectly approximates our shape. We basically have, all the way back here, we basically have this, but this isn't even infinite. This is only 92. If this was infinite, we would have the perfect volume of the shape. Perfect. That's all we have for the notes. And so after you write your summaries, I'm going to come back in the video with a few example problems from the homework. All right, let's work on a homework problem. So this is going to be number 2. By the way, both of these sides you need a calculator on. The front side, they give you the graph. The back side, they don't give you a graph. What's up? Oh, yes. There you are. All right, so we have these two functions, sine of pi x and y equals x cubed minus 4x. We need to find the volume, and this is what they'll always say. They'll say it's a cross section. It's perpendicular to the x-axis. That means it's a right angle. It's a right angle, and it pops out of the x-axis. So that will always be the same. And the main thing is here, it's a square, and we're going to find the volume. So it's essentially what we just did in our last slide. We're going to take our f of x, the top function, minus the bottom function, and then we're going to square that and then take the integral. Most often mistake is, well, there's two mistakes that you can make. One is not doing the top minus the bottom, although it doesn't matter because it's squared, so you're not going to get negative ever in here. And then the next common error, and I think the most common error, is not remembering to square it. So always remember to square it. So how are we going to do this? It's always going to be the integral between a and b. And let's take our time to make this look a little bit neater. All right, so a is 0, b is 2. It's pretty obvious from the picture. So 0 and 2. And we need to do top function minus bottom function. So which one is the top, which one is the bottom? What do you think, Joy?
I think the first one is the top one because it looks like a sine.
Yeah, exactly. So this one looks like a sine wave. It keeps on going and going and going. That is a sine wave, so that is the top function. So we're going to say, remember we need our square bracket out in front, so I'm going to do that square bracket first. So square bracket, and then we're going to do sine of pi times x, and then we're going to subtract this thing. And this is what we have to be careful of, because we're not just, if I did this, I would be doing this wrong. If I did minus x cubed minus 4x, and I call it a day, I even square it and multiply it by dx, that's wrong. Why is it wrong?
It's wrong.
Why?
Because you have to distribute the minus.
You have to distribute the minus. So you can either distribute the minus right here, or better yet, let the calculator do it for you so you can't make a mistake and just put parentheses around it. Either way is fine, but make sure you don't make that mistake as well. So let's go ahead and do this on the calculator. So Wabbit EMU, we're going to open the TI-83. There we are. All right, so how do we enter this? You could enter these as y1, y2, but the much faster way is just going math 9. We're going to take the integral, and we're going to punch in this giant function. So we need a parenthesis first. That, I mean, it looks like a double parenthesis, but that's really going to be the first parenthesis right here. Now we're going to enter sine pi x. Sine pi, and I'm going to be careful here. If I just do pi x, sometimes I've had it not work, so I'm going to be very specific and say times x here. And in the parenthesis for the sine, and I'm going to say subtract, and then I'm going to start my parentheses and say x to the power of 3 minus 4x, and I'm going to end this parenthesis right here. So I end that parenthesis, and then I need to end the parenthesis again for this entire function, and I'm going to square everything in there, so I'm just going to hit the power of 2. Okay, what we've just entered here is a function in the first value of the integral equation, or integral function. Then we have to say with respect to x, and from where to where. We know it's from 0 to 2. From 0 to 2. All right, and what do we get? 9.978. So let me move this over. This is going to be approximately equal to 9.978, and we'll box our answer. And it's always nice to take a step back and look at what really did we just find. What does this thing really look like? Well, obviously it's going to be, I don't want you to draw this on all of your homework, but just remember what you're doing. This thing is a length here, it pops out as a square, and then it has some thickness, and it's an infinite number of squares. So that means down here you're going to have a really tiny square that pops up. If I come back here, a tiny square that pops up, and I actually went ahead and took a look at what that should look like. And so this is the function that we're looking at, and if I bring n, oh gosh, of course it's not going to work. Well, that's lovely. If I refresh, is it going to kill everything? I had it all set up, and then it decided to just freeze on us. Don't reload then if it's not going to save this. Ah, there it goes. This is what it looks like. Let's drag that to the right, and we can see this is what the function will look like. Notice that the height gets really small towards the tips because the distance between the two functions was really small. So that's what we just found. Cool. All right, we have time for one more problem, maybe two more problems. Let's go back here.
Do they eventually meet since they get smaller?
Yeah, they do eventually meet until you have that cross-section here will eventually have a length of 0 by 0, so it eventually ends. Yeah, perfect. Let's go on to another problem. Let's go to the first one on the back. The back is pretty difficult, more difficult than the front, because you don't know which function is on top and what's going on. So I'll give us some time to work on this right now. All right, so if you don't know which function is on the top, is it arctan of x, or is it 3? I don't know which one. Maybe arctan is really big. Then go ahead and graph it. So let's pull up our graphing calculator. Let's plug in, well, 3 is one of the functions, and then the other one was arctan of x, so that's the yellow tan up here, so second tan of x. And then we need to set our window. So what do we want to set our window between? So we know it's always going to be in the first quadrant, so that means our x min has to be 0. It's not going to go into the negative x because that would go into the second quadrant. And what about our x max? So we know that there's going to be this vertical line at x equals 1, which means if I was just doing a rough sketch of what's going to happen, so it has to be in this first quadrant, and x equals 1 is right there, which means I'm going to be bounded somewhere in here, which means my x max should be 1. So I'm going to say x max equals 1, zoom 0. And let me come back here to undo all of that. So it draws that line x equals 3 up here, and that must be tan, or arctan of x. So we know that 3 is on the top, arctan of x is on the bottom. So let's go ahead and set up the integral now. So this is going to be the integral between 0 and 1. And it's going to be, we'll do our square brackets here. It's going to be 3 comes first, and then I'm going to subtract arctan, so tan to the negative 1 of x. And then I end my square bracket, and again this should be squared, and if I do this dx then that is going to be approximately equal to, and then we need to do it on the calculator. So let's get out of this, and we need to do math 9 and then enter all that. So parenthesis 3 minus arc, did I do second? Arc tan of x, and that all of that in parentheses is going to be squared, and that is going to be with respect to x from 0 to 1. And I get 6.612, so this is approximately equal to 6.612. Perfect. I think we have time for one more. So let's go to the very last problem, because that one is a little bit different. It's very similar to so there are 3 on the front, so that means that this was number 4. So it's very similar to 5, 6, 7, 8. The 8, the last problem, 7 and 6. 6, 7, and 8 are all similar to the last problem, so that's why we're going to number 8. So I'll give us some time to think about how to do number 8. So when we find it on our calculator, we get, let's get out of this. This is going to be second quit, and we're going to do math 9. It's the integral of 3 times the quantity of x minus 2, all of that squared, and that thing is going to be itself squared. So, I forgot to add the parentheses. So if you ever forget to add the parentheses, and you add it here, it'll overwrite unless you hit second delete, and that'll insert a parenthesis. So once we have our parentheses around there, then we can square it. Square it, and then we are going to say that is with respect to x from 0 to 4, and we'll get our answer out here, which is, it's actually equal to exactly, so I don't need to do approximately. It's 115.2. And then you can say 0, 0, because we're rounding to 3 decimal places.